recently introduced a new type of energy of a system, the disordered microscopic kinetic and potential energy we call thermal energy. And we learned that we can use temperature to characterize thermal energy. More specifically, we discussed how we can relate the changes in temperature of a system to changes in thermal energy. Let's emphasize here that in the context of the energy principle, thermal energy and thermal energy changes show up as part of describing the system, which, along with specifying the changes in energies in the system, like the change in the kinetic energy or changes in the potential energies, are all added together to give the change in the total system energy, delta E. As we know, all these changes together, the change delta E, must be equal to all of the energy transfers. To this point, we've only discussed one type of transfer, energy transfer by forces from agents in the surroundings transferring energy to or from the system. That is, energy transfer by work. Today we'll discuss a second distinct type of energy transfer that can occur when the system and the surroundings are at different temperatures. This type of energy transfer is familiar to us. Let's say we have some cool water. We'll take that as our system, and we place that water in contact with something at a higher temperature, say a hot kitchen pan. Then we know from experience that there is energy transfer from the surroundings, the hot pan, to the system, the water. This is energy transfer due to a temperature difference, which we typically symbolize using the letter capital Q. Energy transfer in these cases is very different from the energy transfer by the process of work. Notice here, to our eye, the water can be sitting perfectly still with no displacements, so there can be no work done by the surroundings on the system. Instead, all of the action for energy transfer in this case is happening at the microscopic level, where we recall from our ball and spring picture that the atoms and molecules will be in constant disordered motion, and bonds between molecules will be stretching and compressing. Now, when we place the water in contact with the pan, then some of the molecules of the pan and the water will collide with each other. The fact that the pan is at a higher temperature compared with the water means, among other things, that the molecules of the pan will have, on average, a higher kinetic energy than the water molecules. So higher kinetic energy pan molecules colliding with lower kinetic energy water molecules will result in energy transfer from the pan molecules to the water molecules. There are other possible types of collisions between pan and water molecules, but at the end of the day, the high kinetic energy pan, low kinetic energy water collisions play the key role in energy transfer, so that on average, energy is transferred from the pan to the water. Strictly speaking, this is also a kind of work. The pan molecules are exerting forces on the water molecules through some displacement. However, the disordered random way in which this microscopic work occurs is very different from the kind of work we discussed earlier, where macroscopic forces act through macroscopic displacements of the overall system. So, this microscopic work, this transfer of energy by temperature differences, Q, is best thought of as a process quite distinct from the work W. Before we do an example involving the transfer of energy by temperature differences, we need to say something about the sign convention for Q. When the surroundings are at a higher temperature than the system, like the water pan example we just discussed, then we have Q positive corresponding to energy transfer into the system. By contrast, if the system is at a higher temperature than the surroundings, say we place hot water, the system, in contact with a cool pan, part of the surroundings, then we have Q negative corresponding to energy transfer from the system to the surroundings. Notice this sign convention is consistent for both the work and the thermal transfer of energy. Energy transfers into the system are positive, and energy transfers out of the system are negative for both W, the work, and transfer due to temperature differences, Q. We're now in a position to write a more general form of the energy principle like this, where we now have two different types of energy transfer that can happen. This form of the energy principle is sometimes called the first law of thermodynamics. Now, in a given problem where we apply the energy principle, we could have both types of transfer happening at the same time. Here's a question like this for you. Give it a try. Let's start with our fundamental principle, the energy principle. Our unknown is Q, so let's rewrite the energy principle to solve for that. Now we need to find both delta E and W. W, the work, is easy. We're told that explicitly. The beater exerts forces on the water through some displacements such that the total work done by the beater on the water is 50,000 joules. Next, we need to calculate delta E. To do this, let's get a clear picture in our mind of the initial and final states. The initial state is the water sitting at rest, no kinetic energy, before we put it on the stove. The final state is the water again at rest. We have in mind all of the kinetic energy in the water during the beating process was ultimately dissipated and ended up as thermal energy. So the change in energy of the system, delta E, is just due to the change in thermal energy, delta E thermal. Now, since we know the change in the temperature of the water, the mass of the water, and the specific heat capacity of the water, we can calculate delta E thermal. And now we just solve for Q. We will end this lecture with one final note. Energy transfer by temperature differences is also properly referred to as heat. We need to be careful here as the word heat in everyday usage is often used, in a scientifically incorrect way, to mean thermal energy. So properly speaking, when we have an object, our system, that is at times warm and other times cold, we properly say that the object has more thermal energy when it is warm than when it is cold, and we avoid saying incorrectly the object has more heat when it is warm than when it is cold. By contrast, it is proper to say that heat, energy transfer by temperature differences between the object and the surroundings, is one way that the object can gain or lose thermal energy.